3, 2, 1, live. So, as usual, please mark with the plus sign if you can hear me and see this live stream. Perfect. My name is Gregory. I am a Python developer, and I will be our host for today. We at Singula team hire Python developers, teach them, and contract them out for our clients. So we are trying our best to keep our high level of expertise, and we do all kind of events. We help to organize conferences like PyCon. We run these online meetups and do all sorts of activities. And the main idea for these online meetups is not to educate Python developers. We can't compete with Coursera or YouTube or PyCon, but to provide a place where we can discuss things. And after each talk, we will have a live discussion with our speaker where you will be able to ask questions, and I, as a host, will help us all to discuss interesting topics. These talks and topics we highlight are pre-recorded, some in our studio and some at home. Long story short, let's join our first speaker, watch our first talk, and after this talk, speaker will join me live where we will be able to discuss this topic. So, Maria, Spark, and Hadoop.
Hello, my name is Maria and I'm an ML engineer at Megafon. Today we will talk about what difficulties can arise when you are working with cluster and what methods are available to solve them. This report will be useful for analysts and ML engineers. In a large ML team that works with big data scientists regularly face the distributed computing. They work with millions of rows of data and put machine learning models into production. I won't go into much detail about what the Hadoop ecosystem all about. Let's remember that it has 4 main models: Hadoop Common, HDFS, Yarn, Hadoop MapReduce. Today we will talk about configuring the Spark configuration, monitoring Spark application using Python methods, the problem of small Hadoop files for glue on HDFS, and cluster memory. Let's start with this problem. Several users on a cluster can use all the resources, which can influence the work of the others. Despite the fact that each user is limited in resources, this limit is set high enough for complex tasks. In order not to lower the limits, users should use the settings on the Spark configuration parameters. If you don't know how many resources you need for a task, then you should use the basic parameters. Here, max executors, maximum number of executors for dynamic resource allocation, executor cores, number of cores for one executor, memory, the amount of memory for one executor, memory overhead, the amount of out-of-order memory that can be allocated to the executor. At the same time, you need to check the configured dynamic resource allocation. In other words, enable dynamic resource allocation, enable data saving at the shuffle stage, and limit waiting time for one executor. In running the application, you can monitor how many cluster resources you are using. When setting the configuration, the task will consume no more than max executors multiply Spark executors cores of processors and no more than max executor multiply Spark executor memory in the worst case scenario. In order not to register the specified configuration, every time you can wrap it into internal library. So we have defined the main parameters for adjusting the load on the cluster. Now let's talk about monitoring. If you have an access to running application, you can get a report with the parameters of Spark application that you are interested in. This can be done using Python methods. You will need the subprocessor library to access yarn and display a list of applications using the yarn application list command. The requests library to access the yarn resource manager UI, the beautiful SOAP and Ray libraries for the side parsing, and the pandas library for generating the report. This way we will get a data frame that will contain accounts, application IDs, launch URLs and resources used. IDs and URLs are hidden on the picture. Why is this even necessary? Using this information, you can configure triggers for the specific events. For example, some apps can run without performing any tasks. You can use the date of the last completed task of the app to determine the time of its last activity. Even if the app does not perform tasks for a long time, it continues to allocate resources that someone may need. Such application must be stopped. For example, if you exist 7 days of inactivity, you can send a notification to the user or do yarn application queue. Such events can be wrapped in a Docker and placed on the schedule in Airflow. Now let's talk about working with cluster memory. In distributed computing, data in memory is divided into partitions, which are saved as files to the cluster disk space. And it is very important to monitor this saving. In HDFS, each file is stored in 64 or 128 megabytes distributed file system block. The approximate size for storing each such object is 150 bytes. That is, a file with a size of 1 megabyte is stored with a block size of 128 megabyte. Two files with a size of 1 megabyte will be stored in 2 blocks and take up 2 times more space in the namespace, although they could fit in 1 block. Many small files will take up a lot of space on the name node. As a result, there may be the following consequences: inefficient disk space filling, slowing down the speed of completing tasks, workload increasing, performance dropping. When you are writing to Hive, a dynamically partitioned Hive table, each partition is processed in parallel and opens a new file for each new partition key. If the value of Spark SQL shuffle partitions is equal to 200 and it uses partition by in 50 target partitions, then as a result we will get 10,000 files. In order to deal with this, you need to use partitioning methods, which allow you to split data into parts. Apache Spark supports 2 types of partitions: in memory using repartition or coalesce, on the disk using partition by. Therefore, to save the tables correctly, use the following code. First, we apply repartition to the Spark data frame and change the number of files by num files partitions. Then we apply partition by if we want to increase folders to store the files. The difference between coalesce and repartition is that coalesce can only reduce the number of partitions, since coalesce redistributes existing data partitioning, and the repartition completely mixes them up and can increase or decrease the number of partitions. Before saving, you need to check the number of unique values in the partitioning column. If partitioning uses a unique key with 1,000,000 values, the name node will crash. A simple way to check on uniqueness by a column is distance count. To control small files on HDFS, you can configure notification in Airflow for specific folders in the file system, for example, using the bash code. HDFS DFS count with sorting outputs with the lists of the object in the directory with their memory and number of files in descending order by the second argument. But it is quite possible that you need to correct an existing table, and it is not enough just to change the saving method. In this case, you can use Spark hidden methods to implement the file gluer on HDFS. And it may seem like a simple task, but it is not true if you don't know that you need to look for hidden methods. By accessing the file system, you can count, delete, and move files. For example, view the total size of the directory in bytes, or get the total number of files in directory. If you want to change the table, you need to make a resave to the temporary folder and move files from the temporary folder to the original one. Use the copy method to move files. We talked about partitioning methods to maintain cluster stability, but it is also important to control the amount of memory in regular table saving. Add date partition during saving and clear a partition that exceeds the table storage depth using the Spark SQL query. If the tables are already saved without limiting the storage depth, you can configure automated table cleaning using the Airflow and Bash script. This script outputs all objects in the folder, determines the time then the object was created, and deletes files with exceeded storage depth. Then summarize. You need to configure the Spark configuration to control the load on the cluster. You can use Python methods to monitor specific triggers on the Spark application. The problem of small files can be solved using the repartition, coalesce, and partition by. The ability to access the hidden Spark method allows you to edit existing data and implement HDFS gluing. You can monitor the memory usage on the cluster with HDFS DFS. And here you can see my contacts, and now I can answer your questions.
So, Maria, welcome to our live stream. Let's check. Please say something.
Yeah, hello.
Nice. I saw that your recording, it was from one of the Eastern European studios. Unfortunately, I work from the Netherlands and I miss them. How it was to record your talk in real studio with camera, slides, microphone, and all this setup? How is your impression about that?
You have a great studio, but it was difficult for me because I don't practice English enough every time in my life.
Oh, that's
Uh,
absolutely okay. Both, for example, Singula team, the company I'm working at, it is famous for being 100% remote. It was established as 100% remote 15 years ago, far, far before COVID. And actually, all my colleagues, we work from all over the world, and we have all languages, all accents, all time zones. And of course, only a small fraction of my colleagues talk English as their native language. Personally, I struggle with English, and especially I'm not a data engineer. I am backend engineer, like network, APIs, websites, all these things. And for example, when I want to talk about machine learning, I always try to pronounce machine as machine, because most of the English words, we have stress on the first part of the word. But machine, it's a French word, it's long word. And as all noble French words, it has stress on the second part. So, okay, let's discuss things. That's the topic we all gather today. And our guests, please ask your questions using the chat. I will vocalize it to our speakers so we can discuss it. And our first question. You know a lot of low level details about Spark and Hadoop and other things. What is the project you're working on?
I'm working in big data team in a telecom company, and in this team we have projects with a great amount of data, with millions of rows of data, with uh, and we have an Hadoop infrastructure for working this with this data. It's not always pandas or Sklorn, because there are millions of rows. And my projects are about learning machine learning models and deploying MLOps machine learning platform that helps data scientists to work with big data projects.
Spark, it's famous for real-time data processing, and of course, and at telecom, you should have lots and lots of real-time data. So, more questions. Are there any auto configuration tools available for Spark? Because you um, talked a lot about like low level details, how you can configure things, how you can secure things, and all other topics. But maybe there are some auto configuration tools that Python developers or DevOps can just install and then magic. Everything is auto configured.
Uh, I don't think we can configure everything in Spark in auto but in more higher versions of Spark, for example, since third version in Spark, we have some auto SQL auto parameters with in configuration. We can make them true, and we have some auto configuration in our tasks that and we don't need to tune in our parameters. It's different specifics for different Spark versions.
By the way, uh, your company is a telecom company, and for sure you have lots of different IT systems. Do you use Spark as your main data access system, or do you use other systems for same or different tasks? What else do you use for data access, query, and other tasks?
The main is Spark, Hadoop system, Oracle system,
Mhm.
different SQL, Postgre. Um, there are the main apps for big data, but we have different commands because of the big team, and in some commands there are NLP, and they use another systems, I think, but I don't work in this command. Yes. And some commands can work with Excel, Microsoft, because analytics is different. Um, yes.
More questions from our guests. If you are a data engineer and you are targeting some high profile job, for example, a job at Google, which technologies are most important? Which technologies do you think are most important for such a job for a data engineer at Google?
Um, I heard a lot of about Google is a part of Fang, but in my opinion, there are difficult uh, parts of um, algorithms uh, in their interviews, and I think that uh, your hard skills in this uh, way is something maybe not important, but because they have their own systems, like Yandex has a lot of their own systems. And then you go to such great company, you need to be uh, able to learn new technologies.
Oh, yeah,
I
they
think
are
so.
infamous for using lots of local stuff like Alibaba in China, Shopify in the Netherlands, Google worldwide, and other companies. By the way, I really like the next question from our guests. What are the data volumes when you must use Hadoop and Spark? For how long you can use a simple Bash scripts with regular PostgreSQL database? So, how
Mm,
big should be your data for your DevOps team to install Hadoop, Spark, and other shenanigans?
I think we have about terabytes of data. If you have about 50 millions of rows in your data frame, you can't use pandas. Uh, Even if you have 2 millions of rows, it will be difficult to use pandas. You will need mm, some tools to parallelize it. I think it's
Indeed,
about more
indeed.
than 5 millions.
Yeah, I also think it's terabytes of data. Then you need to start thinking about moving to more advanced tools. Anything less, like hundreds of gigabytes, Postgres and Bash, they are perfectly fine. By the way, during your talk, you mentioned Spark tasks and jobs and processes which consume resources. And for a data engineer and DevOps, what are the best ways to find tasks that use too much resources, that hog memory and CPU and make your cluster unhappy in general?
The best way it was its question is about what my um uh, uh, what was I talking about?
Mm-hmm.
uh, we can use only Spark application.
Mm-hmm.
we can use only an open UI in Spark if we want to find an application. And okay, if you want to find something um, fast, you need to parse your UI application, or you can use bash commands.
Yeah, you talked about different APIs and ways. So I think this our question is more about general tools available or something that DevOps engineers can do manually. Yes, UI is somewhat useful.
Um,
Okay, let's wait a little bit for more questions. Do you like actually using Spark? Do you think it's a good tool for the job at hand, or do you think it has some shortcomings and should be replaced with something better? What is your personal opinion about this Spark system?
I like to work with Spark, but I think I would like to have a greater version of it. Um,
Mm-hmm.
and I want to say that I'm not a DevOps engineer. I'm a machine learning engineer.
Mm-hmm.
It's different.
Yeah, completely different, but sometimes DevOps they come to us we need your help to write some code for our systems. Yes, and pure software developers we help DevOps engineers in order for them to solve their job. So I think the last question for your talk will be one more general question. You talked about different approaches and systems you develop, but are there any existing tools available to maintain a Spark cluster, something open source or commercial that you can install, have a nice GUI, all problems and issues listed, and a big green button fix things and optimize things and anything like that. Maybe some new developments in that area.
Mm, yes, there are some applications, but I I can't now remember the name. But yes, there are some applications that you can install, and in your uh, e- especially in your Jupyter, and yeah, you can use them to monitor Spark applications. Mm.
Nice. Maria, thank you a lot. It was a pleasure. See you later as a guest to our meetups. And if in some future you have more interesting topics for Python developers or other developers, because Python is not the only singular meetup, please, you know our call for papers button. See you later. Bye bye.
Bye. Thank you.
So, and now our next talk. This talk was recorded by me, actually in this home studio, not the best microphone and chroma key. I am trying my best, and maybe in a few months I will improve this setup. But now we will try to withstand my severe Siberian accent and talk about why our beloved language is so slow, and what we are doing about that. Hello, and thank you for joining me. My name is Gregory. I'm a head of developer relations and a Python developer at Singula team. We do mostly out stuff. We hire developers, teach them, and contract them out to our clients. And our clients, they are different businesses, small businesses, medium businesses, big businesses. And they have what is called business need. And within such a business need for software development, there are biases about the best technology. They think that if they need some backend development, it's PHP or maybe C# or Java. And for ML, they prefer Python. They prefer front-end for JavaScript development and Ruby for full-stack development. But if we look at top 50 Y Combinator startups, the picture is different. Most of successful startup companies, they use Python and Ruby. These languages are different, but they have one thing in common. They referred as slow languages. And that's my topic for today, why Python is slow. And I want to unfold this topic starting with how a modern CPU works. The electric impulse travels through CPU cores, and these cores, they try to execute as many instructions as possible, a few billion times per second. And as many as possible is a key term, which means CPU speed is how many instructions it can perform per some interval of time. And each core, it tries to perform as much instructions as possible. It reads instructions from memory, and instructions, they are mostly simple. They are math, branching, memory access, and this memory, it's cached between registers and physical memory. And the difference in access time is more than 100 times. That means the speed of our code is how it handles memory. And memory is handled differently by different programming languages. It can be handled manually, like in C++ or Rust, where we developers allocate memory, access memory, deallocate it. Or we can use garbage collector and compile our language based on types like in C# or Java. Also, we can avoid using types but still use garbage collector by compiling a very simple language like a JavaScript or Lua. There is one more alternative. We can use virtual machine that will handle garbage collector, and no compilation is required. Such approach is used by Python, Ruby, PHP, and many languages. Virtual machines, instead of compilation, they handle memory, allocation, deallocation, access. They handle object types at runtime, and they provide rich language semantic. For example, with the Python programming language, we can easily change how negation works for our type, and all our code works completely different now. Virtual machines are known to be slow. And let's see, Python. It handles memory, it handles object types, it provides a rich language semantic, and it uses a virtual machine for all these tasks, which is slow. But wait, not all languages that use virtual machines are slow. For example, JavaScript programming language, it handles memory. We do not need to allocate or deallocate memory in JavaScript and in Python. It handles object types. We do not need to specify any types within our source code. It provides a rich language semantics. Ask any JavaScript developer, is the language good? And they will answer, yes, it's an amazing programming language. It uses a virtual machine for all of these tasks, and it is very fast, comparable in speed to C++. One of the points is a lie. Actually, it's about richness of JavaScript semantic. It is not a semantically rich language. And the secret of JavaScript speed lies within its V8 virtual machine with just-in-time compilation. This simple semantic allows Sun Hotspot JVM team to create a really fast virtual machine. And this team, it was led by Lars Bach, who basically create virtual machines for his entire career for 25 years. He is the world leading expert at creating virtual machines. He made them in Sun and now in Google. So this virtual machine is an expensive one-time miracle created by a top team of software developers. And now they have issues because JavaScript language, it evolves, and within which this evolution offers, they want richer semantics, and V8 development team, they like, oh, if we add this to the language, that will slow things down. We cannot add it. Please help us, anybody. That's the issue with just-in-time compilation. But 100 times slower. What if we add just-in-time to Python? There are such projects available. And just for reference, if we take some synthetic test, which C++ handles within 20 seconds. The normal implementation of Python took more than 3 seconds for such task, which is more than 100 times slower. By the way, same numbers are with Ruby. But if we enable JIT, just in time, using PyPy, for example, it will become 10 times faster, not 100 times, but 10 times. And again, comparable times are with Ruby. These tests are synthetic. And for big projects like number crunching, machine learning, big code bases with hundreds of thousands lines of code, enabling just-in-time compilation is not a silver bullet, and our code, it can be faster, like 2 times, 3 times, but not 10 times, with compatibility issues. So most Python developers prefer not to enable just-in-time compilation and live with a language which is 100 times slower than C++ because of its rich syntax and semantic. How do we live with such a slow language? First of all, native extension. GIL, Global Interpreter Log, that is used by garbage collector to provide a rich semantic. It limits on how our Python code can execute with threads, how it can scale. But with native extensions, they are written in C++. They raise global interpreter log, and they can work simultaneously, processing numbers, images, data, audio, video. There are thousands of libraries written in C++ that can concurrently handle CPU-intensive tasks. This is the main way for the Python developers to cope with the language being slow. The language itself, it acts as a high-level glue that glues together different native libraries, different high-level primitives, and for example, by writing some API with fast API framework with some JSON handling libraries, most of the code being executed, it will be a very fast C, C++, and Rust code of these libraries. And our Python code, it will only provide high-level instructions on what to do. And with modern Python, with native extension, it scales pretty well with processes and threads within a few servers. We can achieve hundreds of thousands requests per second. Servers are cheap and developers are expensive nowadays. Also, async await development is on the rise, which allows to use non-blocking Python code where we access some network resources, and Fast API can handle hundreds of thousands concurrent connections within one server, which is an impressive number. What are natural targets for our language glue? First of all, machine learning and data science. They are natural targets for Python due to its history. 30 years ago, Python was created as a language to be used as a high-level glue, and it settled within academia. And through the years, it was promoted by scientists, making each new generation of scientists to use Python more and more for their everyday tasks, because it's a nice high-level glue. It's compatible with existing native code. It can call existing native code, use native extensions. So after the development of more and more elaborate machine learning and data science solution, obviously they were developed in Python, and now Python is the default language for such tasks. Also, it's a default language for tests, for automating testing, for browser manipulation, for any kinds of automation. That rich semantics and easy syntax that I previously mentioned allows new developers on board to Python very, very fast. So it's an ideal language to teach people how to develop software, and they can use this knowledge to do automated tests. Also, all backend development with non-custom number crunching is great with Python due to support of libraries, abundance of them, and native extensions which are readily available for us. What does the future holds for our beloved language? First of all, lots of research is being made right now regarding the language speed. For the sake of machine learning, we are fighting with global interpreter lock, so many Python threads can concurrently access gigabytes of data stored in memory in one process, and there are two projects to tackle that. First of all, it's the GIL removal project, which will be available in a few years. It's a work in progress right now. And secondly, it's the Python sub-interpreters, which will land at the end of this year in version 3.12. By the way, Ruby already had interpreters a few years ago, and that project was not successful because sub-interpreters means that many threads within one process have each own virtual machine, and then they can access read-only shared data, but they cannot access that shared data for writing by default and need special API for that. This means that all libraries that share data between threads is incompatible with sub-interpreters by default. Also, the implementation of sub-interpreters in Ruby, it had the same global interpreter log for all threads. And garbage collection, memory management, it kills performance gains very, very fast. I don't know how sub-interpreters will be implemented in Python 3.12, and we will learn it at the end of the year. And what I want to discuss after this talk. First of all, is it even viable to create such languages with rich semantics that are slow? Maybe we need to focus on languages that are not so rich, not so easy to use, but extremely fast. For example, Rust programming language. And what about prices for computation, comparing them to salary of us software developers? Maybe servers are not so cheap nowadays. Second, I want to discuss this take on rich semantics that Python uses with the focus on really simple syntax available for new software developers. That is not the only way, and for example, in Ruby, it's also a very semantically rich language, but the syntax it's complex, it's hard, it's not for new developers, but for experienced developers. Such syntax allows to write less code faster and with more meaning. What about monolith and microservices? Right now I can see that companies, teams are moving back from microservices to monolith because we already know how to separate concerns in our big source code bases, which does not require microservices separations. I also want to elaborate about languages like C Sharp and Java, which also uses garbage collection, but instead of Python, they use compilation instead of virtual machines. And for that reason, they cannot add rich semantics and be as good as Python for everyday use. Or can way. With Python, we also have types, but they are optional, gradual types that allows us to set specific traps only in parts of our source code which are important for us. How viable is this approach? I can see some teams misuse, overuse, and abuse types, writing more type-related code than business code in Python. These and more topics are for us to discuss right now. Thank you. Oh, thank you for listening to my corrupted English and constant misuse of machine that I just can't remember. I don't know how many years should pass before I will be able to pronounce machine instead of machine most of the time. Okay, so let's discuss things. I have no guest speaker with me because I am the speaker. So I will act both as a host and a guest for this part of our online meetup. And our first question is if JIT, just-in-time compilation, is so good, why it is not built into Python programming language? The latest interview of Guido van Rossum to Lex Freeman, if I remember the name correctly, they discussed this question in details, and I highly recommend this interview to watch. It's really great. And the idea is that just-in-time compilation for such rich language, it need to guess how dynamic code is working right now, what shape it has, in order to create a best possible machine code for it. And if this compilation, this process of best guessing, guess incorrectly, or the code changes at real time, it will be not a speed gain, but speed decrease. So implementing just in time in Python language itself will make like most of the code 10 times faster, but some fraction of the code 10 times slower. And such a language that is used by millions of people all over the world. Developers just can't break compatibility that way. Maybe in the future, JIT will be added as an optional flag like it was done with Ruby, but right now adding it to the language, it's not valuable. So, next question. Expecting Python to be fast isn't like expecting cheap Toyota to be as fast as Ferrari. Often by trying to build something the best is everything, you get something what is meant in everything. Yes, but I'm not only a Python developer, I'm also a hobby neurophysiologist. And as a scientist, I like to answer why. So it's obvious that not all languages fast and have rich semantics and easy to learn and popular and blah, 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 blah. But I like to answer why. Why Python is slow. Why we can't have both rich semantics and fast language like JavaScript, for example. And by understanding these implications, we as software developers can write better code, can use native extensions when it's required, can use JIT when it's appropriate, or can use microservice architecture when it will provide much better speed gain for our solutions. That's why I recorded this topic to give a better theory about the particular reasons why Python is slow. Not advocating that it should be slow or should not be slow, but just explaining things why it is so, why JavaScript is fast and Python is slow. 10 years ago, that bugged me a lot because for me, then, these languages are very similar. Now I know that the semantic of Python is much, much bigger compared to JavaScript. As exampled in my talk, you cannot override minus operator for some JavaScript object in real time with such consequences. But 10 years ago, it was unclear for me. So, what is your opinion on Python introducing some characteristics of a compiled language like C++? If you are talking about types, the main characteristic of compiled language such C++, Python uses gradual typing, and it actually popularized gradual typing, and I think it's great because in C++ or Java and or Rust we can write types, and we are obliged to write types. We should write them. We cannot write C++ code without types. And with Python, we can write our code with or without types. This allows us to have best of both worlds. Of course, right now, types are not used in Python JIT systems to optimize Python code, but still, it's a great support for us because types in our Python code, they allows us to catch our errors later. So when we write our code and we have idea what we are writing in our mind, we can put types as traps for future us to help us in the future. But we can put these types optionally, gradually, only in some places. And good Python code, it is not like sprinkled with types all over the code. It contains types only in places where they really help to catch errors. And that's great. Also, manual memory handling. Uh, right now, I can't say that Python has any manual memory handling. It's all automatic. All our containers, they are absolutely flexible. We can take a list or dictionary, put one item inside or millions items, and it will stretch according to our data. We do not need to explicitly allocate or deallocate data. So it's mostly types, not manual memory handling. Whereas this new language, Mojo or something like that, that tries to unite both Python and C syntax and allows optional low-level approach, but it's still in alpha, and I don't know how it will unfold. Why exactly big projects are not so fast with just-in-time compilation? That's a tricky question. I tackled it a little bit in my talk, but just a little. Actually, it's counterintuitive. Why? If we take a big Django project with 500,000 lines of code, uh, enable JIT with number or PyPI, and we can have no speed increase. We can have 2 or 3 times speed increase, or we can have actually speed decrease. It's absolutely unclear why it is so. For most synthetic tests, JIT, it's always a great like tenfold speed increase. But you see, big projects, they are big mostly because they contain lots of business logic, of complicated business logic written with complex dynamic Python with DSL, with meta classes, with decorators, with lots of dynamic things. And all these things, while compiled to native code, they produce heavy overload. They produce machine code that requires to do lots of checks in real time. It's not a simple JavaScript code. It's some complex Python code. And due to the sheer amount of these code objects it produces, it's also a heavy load on memory and on cache memory. Uh, uh, Big Python project normally contains tens, hundreds of megabytes of data it works with. This memory, it doesn't fit into cache. So even if we enable JIT, we gain no big performance gain because our code is much bigger compared to these small synthetic examples. Bigger by memory, not by amount of lines of code. That's oversimplified reasons. Of course, there is more, and I'm simplifying things, but that's an overall impression why big projects do not gain such speed increase as our synthetic tests. So, our next question. Why is Python only 10 times faster with just-in-time compilation while JavaScript is 100 times faster compared to some non-JIT JavaScript versions and comparable to C and C++ in speed? That's mostly rich semantics. Even the Python code that doesn't use meta class, shenanigans, attribute access protocols, and other advanced things, it still checks lots of things in real time. Because at any moment, we can take any object, any class, they are objects in our world, change something like dunder add or dunder get item or dunder something, and that changes the behavior of all objects in our code. So we cannot produce simple, straightforward machine code for these objects. We need to add lots of conditions into the code being generated by JIT. Normally, these conditions are handled by virtual machine, by the native code of Python virtual machine. Machine. Oh, the Python virtual machine. But if we compile our code into the native code by just-in-time compilation, we need to put all these conditions and tests and checks into our generated code, making it like 10 times slower compared to a straightforward C++ code that can use types in order to always know how do objects behave. What is a simple way to make some Python code significantly faster when speed is required? I think the simplest way is to just pip install and import number and use number decorator on some function. This will dynamically enable JIT for this function. This will compile function in real time into machine code, into some fast machine code. And this can make our code 10 times faster or break our code if it uses some advanced technologies which are not 100% compatible with JIT compilation. But I think that installing number and enabling it for some Python functions is a great starting point. And later you can use PyPy project to enable JIT for your entire code base, or some specific tools like Cython to write a subset of your code into Python-like C, which will be guaranteed to not fail, but some Python features will be not available. Okay, let's do the last question of this session. Are native libraries like NumPy always fast? Actually, it depends how we use them. Because if library is self-containing, like, for example, image processing library, if we use some image processing library, load some file, give it to our library, and then like resize, apply some fancy filters and save to disk, it will be extremely fast. But if after using the library, we need to somehow access the resulting data from Python, there are challenges, because depending on how we want to access such data, we can greatly slow things down. For example, if we transform image using some library that's very fast, and then we get bytes, it's very fast. But then we iterate over bytes, and for each byte we do some Python code with if and with transformation. That will be slow. So like transforming image will be a few milliseconds, and iterating over image bytes and doing some simple checks in Python will be like hundreds of milliseconds. That slow. So it's important not to pull lots of data from native world of libraries into Python world of objects. It's best to communicate between native libraries with like bytes arrays or like NumPy arrays, so no data is transformed into Python objects. That's it. Okay. Thank you a lot. And now our third talk, Alexander will highlight a topic of feature engineering for spatial geodata, maps, and all these things. Let's join Alexander, and after his talk, let's discuss it with him.
Dear colleagues, my name is Alexander Meshcherkov, and I currently work in Cinemax Data Lab. Data Lab is a company which provides services in machine learning development and integration. And I want to share my knowledge connected with geospatial data. I had a lot of thoughts about how to structure this presentation, and I decided maybe not to make it short, but at least simple. I made it as a cookbook. So if you want to choose any sort of your features which are appropriate for your data and for your geospatial data, you can use any part of this presentation in order to add new features into your data set. And today we are going to discuss which ways we can obtain our geodata. Secondly, we will discuss which type of features we can generate based on shapes and geometries. So we also discuss how we can aggregate our data, and finally we will discuss which features we can obtain using knowledge of spatial patterns. So, how to get geodata? There are a lot of different services which provide geodata. For example, Google Maps or Yandex Karte, Yandex Maps can provide different sorts of geodata. But if you want to get open source solution, OpenStreetMap is the best one. So, you also can find different types of geodata on Kaggle. If you don't want to set up OpenStreetMap database, but if you want to make a stable and reliable solution, I think that OpenStreetMap is pretty good for such task. How does this data are collected and kept? We usually use well-known text format. What does it mean? Well-known text is a type of format which describes polygons, points and lines in the way of strings. So, for example, we can describe points, line strings, polygons, and different type of combined geometries. For example, multi-points, multi-line strings, multi-polygons, and geometry collection. The main rule is to keep such data in a way when you can collect similar data in the same table. For example, points with points and polygons with polygons. In these cases, you can face geocoding tasks based on transformation of address tracks into points. There are also different types of services, for example, Mapbox, AirGIS, Google Maps, but the free solution and open source solution is Nominatin, which can be placed on your local machine and use its resources in order to transform addresses into points. In many cases, you can use only coordinates in order to get some features. For example, you can see different regions based on the road density. So you can see pretty obvious geospatial correlation. Regions placed in the northeast usually have less road density than places on the southwest. So, if you use only latitude and longitude, you can describe road density in this way. First of all, you have to know how to transform different geometries into different types of polygons. For example, we can use buffer. Buffer is a pretty common operation which allows you to expand borders of your polygons or lines or even points. So it usually used, for example, in such cases when you want to aggregate data. For example, if you want to make features based on quantity of points nearby, for example, your current point. You can also transform your polygons into different types of shapes. For example, you can obtain boundary rectangle or convex hull. What does a convex hull is? It is a convex hull is a specific shape which slopes to it doesn't intersect its sides. So if you see different shapes which slopes intersects its sides, these places are named convexity defects. So based on such areas of polygon, area of convex hull, area of bounding rectangle, you can obtain different types of features. For example, if you use area of your polygon and area of your convex hull and obtain ratio between them, you can get solidity. This feature describes your polygon in terms of convex defects. If solidity equals 1, so such a form doesn't have solidity defects, and it equals to convex hull. Also, you can get orientation of your polygon and extreme points. But in many cases, polygons and shapes doesn't give information by itself. Also, you want to know its relationships with each other. For example, Waldo Tobler's first law of geography says that everything is connected with everything, but more close things are connected more than distant one. In order to make an example of such law, we can take a look at the map at the top. You can see two different hospitals, general one and the infectious one. You can see that it also have a different type of building connected with medical work. For example, pharmacies or medical student dormitories. At the bottom, you can see an example of small city, which is there are different type of buildings around one specific area. In this area, you can see all building, which usually people need for normal life. For example, doctor's office and church or shopping mall. So, this law describes our human behavior when we try to place different objects with the same theme or the same subject in the same place. For example, we like to visit places where a lot of shops, for example. Or we prefer to visit a hospital and see a pharmacy nearby, etc. And also we prefer to communicate with people who have a lot of in common with us. For example, poor people prefer to communicate with poor people, or rich people prefer to communicate with rich. And developers and data analysts prefer to communicate with the developers and data analysts. So that's why we are here. In different libraries, there are a lot of different ways to make spatial joins. For example, spatial joins based on the intersections or a crossing or a relationship between two objects when one object is within another one. Why else we can use such spatial joins? For example, we can see a real-life problem of tessellation. We faced it on a real project when we had to make tessellation for Russian Federation. So Russian Federation is a big country, but its area not very populated. Only 20% of Russia is populated. So we made our tessellation based on cities and towns. And when we performed exploratory data analysis, we have seen that there are different defects in our tessellation process. For example, you can see intersecting polygons. Such intersections are pretty harmful for our analysis and data. When we want to aggregate our data, we prefer to choose only one polygon, but not the both, in order to not to duplicate our data. In many cases, centroids are appropriate for tasks, but sometimes a centroid can give pretty misleading information. For example, points of the centroid can be placed not on the surface of the polygon. And sometimes you have to make points which are placed on the polygon. So you can use specific functions which can describe points on the surface of polygon. So we are talking about how to make different spatial joins, how to make points from polygons, but mostly it doesn't describe relationships between points. We also can use different types of distances. There are three types of distance. The most popular and the most common is planar distances. It is pretty simple. It's just a linear distance, for example. And in some cases, when you use such distances, for example, in small towns or on a scale of one street, such distances doesn't give a lot of errors. But when you increase your scale, you can face a problem which is connected with the projection of Earth plane of Earth surface on the plane. You have to know every time you use Euclidean distances on your geodata that every map is a projection of Earth's surface on a plane, and it gives different type of distortions. For example, you can see Mercator's projections. It gives pretty serious distortions on the poles. For example, you can see a face of a person which is distorted in the same way as Earth on Mercator's projection. So if you see maps with a Mercator projection, you can figure out that Greenland, for example, has the same area as Africa, but in reality it doesn't so. So there are a lot of different types of projections. For example, stereographic projections have the least distortion at the specific place. For example, if you want to estimate distances in a large city or in a small country, it is pretty okay to use stereographic projections. It's also pretty common in use for data placed on the poles. So also you have to know that every projection and measurement system has its own spatial reference identifier. Spatial reference identifiers are developed by European Petroleum Survey Group, and if you want to analyze different types of geospatial data, you have to find out which SRID is used in order to make specific projection or deprojection operations. And it is important to know that different types of libraries and programs provide you different tools in order to make projection and deprojection operations. For example, you can deproject objects from a specific plane into, for example, 3D data. One more way to measure distances is using geodetic distance. The easiest way to estimate geodetic distances is Haversine distance. So it is the distance of arc on the circle. It usually gives measurement error approximately between 1 or 2%, and in many cases it is okay, but sometimes, for example, if we are talking about large distances between different countries, it can be pretty deteriorating. If you want to estimate accurate distances, you can use different types of Earth models. For example, you can use World Geodetic System 84. It describes Earth as geoid with the center of mass in the center of the coordinates. That axis connects two poles. X-axis placed on the zero meridian, and y-axis is orthogonal to this plane. So, geodetic distances are distances as the crow flies. They are the nearest distance you can estimate. But we are not birds, and we cannot avoid different types of objects, buildings, valleys and hills. So we usually use different types of routes. So you can also use route distances, the third type of distances. And in order to make route distances, you can use different types of services. For example, you can use OpenStreet routing machine provides you an opportunity to measure different types of route distances. So you can make route distance for example, public transport, for car or for bicycles. So now we're going to talk about point aggregations. You can use at least three types of aggregations in order to make your features. For example, you can use administrative division, especially when it connected with a business problem. But in many cases, it is not very convenient because different types of areas, regions, or countries have different area. You also can split your area using square tiles. It is pretty convenient because you can provide isolation in a pretty simple way. You just need, for example, the set of different longitudes and latitudes, and your tiles are ready. But unfortunately, this type of isolation doesn't provide you a convenient way to find adjacent polygons. You have to use 2 iterations in order to find all adjacent polygons. In this case, a hexagonal grid is more convenient. You can just get all hexagons on the sides in order to find adjacent hexagons. You can use buffers in order to make features based on nearest points and count of nearest points within radius. But you also can make features based on how much points you can reach, for example, by a car or public transport. Probably you won't use a car if you have a shop placed in the front of your home. So you can use different types of rings in order to aggregate points. But you have to know that you need to normalize such count of points by area, because if you increase inner radius, it also increases area of the ring if the width of band is the same. So it is better to normalize increasing number of points in order to make appropriate feature. And we are going to talk about pattern evaluation. There are 2 different algorithms to find hotspots. The first one is gettys or star. It is a pretty simple and convenient algorithm which gives you information about hot spots and cold spots. And local modens I, which provides you not only information about hotspot but also about outliers inside of such hotspots. In many cases, you would use gettys or star, just because it is pretty convenient to calculate, and it takes less resources in order to make such features. And local modens I commonly used for more in-depth analysis. I want to share you a story which inspires me in learning geospatial analysis. And it also shows an importance of hotspot analysis and how you can use, for example, local modens I in your different tasks. It is a story about Jon Snow. Jon Snow doesn't participate in Game of Thrones, but it participated in game of life and death with cholera. He was a British physician who have figured out that cholera is a waterborne disease. He found out a way of transmission of such disease. Cholera was a pretty common disease in London, and it took a lot of life in 19th century. So, before discovery of Jon Snow, no one knew how does this disease transmits. So this person visited every building which had patients with cholera, and counted how much patients were in different buildings. So he figured out that there is a hotspot. This hotspot was placed nearby the pump. This pump was infected by cholera. But more interesting that also on this map you can see an outlier, low-high area, which is a brewery. So I hope you give us an answer why does people didn't use pump in the comment sections. So you also can use clustering in order to find different type of patterns. You can use comments or you can use dbscan. I think that dbscan is more appropriate for geospatial tasks. First of all, dbscan logic is more close to geospatial data, and secondly, you don't need to choose how much clusters you need to provide dbscan analysis. Also, kernel density estimator is not only the way to visualize your data. It's also a pretty good feature which describes how many points are placed nearby a specific point. You can use sklearn in order to define density score of your data and to make a good feature for your analysis. Dear colleagues, this presentation is over and you can leave your questions in online chat, and I hope and I want to give you a proper and fast answer. Thank you for your attention, and I'm ready for your questions.
Alexander, please unmute yourself.
Good evening, my dear friends.
And welcome to our live translation. Are you using some Bluetooth headphones?
Yes, I do.
Actually, they are not great for transmitting your voice. They are mostly for transmitting music into your ears. If you are in some quiet place, can you please change to the microphone of your laptop?
Just 1 second. I'm extremely sorry. Okay, maybe
That's much
better.
better. Yes, advanced conference tech never use Bluetooth headphones for recording sound. They are for transmitting. And thank you for your talk. It was a pleasure to hear. Your English is orders of magnitude better than my own, and you pronounce machine something correctly each time. And I am still learning, like I'm learning for more than 10 years to pronounce English words, but with unfortunate results. Okay.
Probably we had a little bit different. Sorry. Sorry for interrupting you. Maybe we had a little bit different experience of communication with machines.
So let's see, what questions do we have? What Polygon features do you use the most in your own projects or your company projects? What are like top features that are of practical interest?
So a pretty interesting feature connected with Polygon features maybe is just area. So you can calculate area of feature of polygons, and it can be some sort of proxy feature for example, population properties and demographic properties of local area. For example, area of accommodation buildings can help you to define how populated this area, for example.
That's great. By the way, your knowledge about geodata is really huge. What are your main projects? What do you use this knowledge for?
So, application for such geospatial analysis are pretty broad, but personally, I mostly was connected with insurance tasks and and now I am on a project connected with healthcare, and I hope it is going to be perfect. Just because
Yeah.
I like healthcare and medicine, I have some pretty specific background, so it is interesting for me.
Our next question. During your talk, you referenced OpenStreetMap a lot. Are there any shortcomings of OpenStreetMap data, or is it perfect for any use?
So it is not perfect just because it is a service based on users' data. So each user can correct or delete or add new data to OpenStreetMap. It works like Wikipedia mostly, and there are a lot of stages of validation, and some specific users validate other users' data, but sometimes some mistakes can appear in your data, in your input data, and it is a good practice to firstly validate input data by your own, just because everything can happen, and as you know, garbage in, garbage out principle, it is better to avoid it in the beginning.
During your talk, you discussed lots of features that are available on maps, like popular building types near and in, or this medical story about how the connection between dread cholera and water sources was discovered. So, from your personal expertise, what is the most unusual map feature that you encountered personally? Like, what is this?
So maybe not just a feature, but it influence on model. Sometimes it is interesting to figure out how, for example, pub distance can influence on, for example, amount of car crashes. Or, for
Hmm.
example, as a uh, another example, not just a connection of feature and model. Some pretty specific features are connected with isochrones. It is a specific shape which which encircles area in which you can reach different objects, for example, in the same time. So
Hmm.
it is connected with root distances, and it is pretty convenient for in-depth analysis when you want, for example, avoid specific situation when, for example, you include points from the other side of river, and you want to
Hmm.
separate them, just because people can't reach other side of river by their own feet.
Yeah, reasonable. River paths, they are close on the map, but unfortunately, they can be quite unreachable for us. By the way, shameless plug. If you watched us this long, please like, maybe even subscribe. It's needed for YouTube algorithms to promote our live translation to attract more Python developers. So we have more interesting questions and maybe speakers. So this is not for us as a company because we do not make any money from these activities. It's for community, so we can attract more viewers and we can have more questions. But we still have some questions. For example,
Mhm.
can some person download and work entire OpenStreetMap data on their laptop? How big it is?
So, as far as I remember, it is a whole OpenStreetMap data for the whole Earth are, as far as I remember, 124 gigabytes, and it is pretty large amount. And if your laptop allows you to operate such data, okay, you're welcome. You can uh, download dump and to uh, use it in, for example, Postgres application. But in many cases, for example, you it is better to use subsets of such data, for example,
Mm-hmm.
for specific region or only for one country. Also, you can
Yeah.
use API, and you can get any sort of data you want with API.
Yeah, and regarding APIs, are there any good online APIs to make queries related to geodata? Maybe some inexpensive or even free services that you can use to programmatically ask questions and do not download data to your own servers or devices.
So, um, as I previously mentioned, OpenStreetMap has its own
Mhm.
API, and you can freely use it. It is an open source solution. Also, about limitations, there is a previous limitations that some data can be operated by other users or maybe inaccurate, but it is a good solution when you want to follow open source principles. And if you want to, for example, use your data right now on flight without buying some licenses or some applications. And some more limitations, API of OpenStreetMap allows you to use no more than 5,000 of objects.
It's reasonable. Open APIs, they normally have some limits. While we are waiting for more questions, personal questions from myself, for our guests and listeners of this translation who want to start working with geodata, which resources, maybe books or websites or something that you can recommend for new data engineers who want to tackle geospatial data?
So, uh, to be honest, I'm a sort of autodidact and I try to find information by myself, but I also know pretty interesting and informative book. For example, Eric Wester's book about geospatial. It is not about a geospatial analysis, but it is about geospatial applications. It is not a. It is a little bit different from our task, but you can also focus on this book and figure out some basic principles of geospatial data. And also, I and our colleagues, we are editing our incoming uh, article, series of articles in LinkedIn, and I hope it will be a good supplementary material for current meetup.
Alexander, thank you a lot. Please join our other meetups as a guest, and if in the future you will have other topics of interest to discuss, you know where our call for papers button is. And for everyone else who wants to hold their talks here with me, the link will be under this video on YouTube. Thank you, Alexander.
Thanks a lot for.
And thank you all for joining us. My name is Gregory. I am a developer relations at Singular team. We do custom Python development for our clients, and we try our best to give back to the community by organizing such events. Please like, subscribe. This will provide more visitors and much more interesting questions. So, see you later. Bye bye.